So now it's time to welcome Stefan Haacke. So he's coming from the IPCMS of Strasbourg, and he's been working in ultrafast spectroscopy for years for different applications, fundamental science, energy, and biological applications. Please.
Yeah, thank you. Thank you very much for the nice introduction. Yeah, I hope your head is not too much, or your brain is not too much twisted now after all the chirality. Let's come back to, yeah. I'll talk a little bit in the line of what Leif Hammarström indicated. I will try to give you a few examples. Yes, okay. On how ultrafast spectroscopy can really serve for looking into all the photochemical mechanisms, photochemical steps which are important in different contexts related to light energy conversion. So here, I will basically introduce different examples from our research over the last 15 years with different chemistry partners. Our lab in the Institut de Physique and Chemistry of Materials in Strasbourg is physics-based. You will see the members in a minute. But all these collaborations, be it about iron complexes, where with different chemistry partners in France or in Germany, or here the molecules for transparent solar cells with Fabrice Audobel and Frédéric Sauvage in France. A few first announcements. Our team, Biodin, is one of the members for the open user facilities. You'll find our poster here on the left-hand side if you leave the room. These are the laser sources which are available. We perform ultrafast transient absorption and fluorescence spectroscopy in the UV to near infrared spectral domain. Jérémy Léonard is a permanent member of the team, as well as Alexis Boyer. She joined our team this year, and she will develop femtosecond photoelectron spectroscopy. Yeah, these are the different axes of our research. Retinal protein isomerization in retinal proteins is still active. Margaret and I started this together with Margaret 25 years ago in Lausanne. That developed into biomimetic photoswitches. I won't elaborate more on this. We will go into detail here on this axis on photo energy conversion, photo-iron-based photosensitizers. Yeah, so can iron 2 be the new photosensitizers? And what about these transparent solar cells? How can you make solar cells without light absorbing? Without having them transparent? And I will also, of course, indicate the link with the Moonshot project, energy and environment. Yeah, can iron 2 be the new photosensitizers? It's all about making photochemistry with earth-abundant metals. Leif also talked about this. Ruthenium is known as a photosizer here. Michael Grätzel with his well-known dye-sensitized Grätzel cells use ruthenium together with a palladium photocatalyst to make hydrogen generation, two-step proton reduction. That is all demonstrated, works well. So yes, one can say that these metals, ruthenium, iridium, platinum, palladium, are gold standards, but they are extremely rare, extremely expensive, and all these technologies have not made it really to on a large-scale development. So there are many chemists who work now since more than 10 years on implementing these photochemical functions with earth-abundant metals like copper, zinc, chromium, and iron. Why not? Why not? You will see. It's extremely difficult because the energetic structure these in these 3D metals, is very different from ruthenium. The fact is simply that it's all about the energetic structure. What I didn't say before is the photochemistry works with the electrons on the ligands. So the photoexcitation promotes electrons from the metal onto the ligands, the so-called metal-to-ligand charge transfer states, and the electrons have to stay there for typically a nanosecond for the photochemistry to occur. So that is easy in ruthenium because the excitation goes in one of these metal-to-ligand charge transfer states. Very rapid relaxation to triplet state, but here these so-called these are states where the metal center, these are the states where the electron will fall back on the metal. They are higher in energy, will not be reached. So the lifetimes here are in the hundreds of nanosecond or microsecond ranges. But in iron, this is the typical iron bispyridine complex. Here the ligand field splitting is much smaller. These metal center complexes are low in energy, and the lifetime here on the triplet state is not longer than 50 femtoseconds. Marget showed this. McCusker, Collet worked a lot on these different systems. This is simply, it comes simply from the fact that the d orbitals on this iron are much smaller, really, than in metals with more, when you're talking here about the 4d or 5d electrons. And in these smaller 3d d orbitals, simply the electronic interaction with the ligands is less. And so one talks here about the ligand field splitting, this difference that is smaller. Yes, so there was a partial breakthrough in that area more than 10 years ago. Kenneth Wernmark in Lund was able to design here these iron complexes with coordinated here with carbene. And these carbene ligands provide much more electron density. It was able to increase the ligand field splitting, but not really shift these metal centers upwards. But nevertheless, instead of 50 femtoseconds, the lifetime now was 9 picoseconds, but still too low to make really photosensitizers of it. Nanoseconds would be the aim. And so, there were different approaches to design new molecules with more sigma-donating, pi-accepting ligands. With Philippe Gros, he had the idea, we could enhance the conjugation on the ligands and stabilize the MLCT states. Okay, we can gain here 7 picoseconds. It was shown that you need at least 3 carbon dots in order to come into the in the picosecond range, but it was always, these lifetimes were always limited by the lower lying MC states. So the one parameter that is important is the ligand rigidity, because the transition from ligand centered to metal centered always enlarges the molecule a little bit. And here is a very nice proposal 2 years ago from the University of Illinois with these very rigid ligands. Doesn't need to be a very complex pyridine moieties. Lifetimes of nanosecond were obtained. So it is possible. But okay, I will come back and say here is what the femtosecond spectroscopy allows us to characterize the excited state lifetimes. Philippe Gros had the idea to replace the pyridines by pyrazines, extend here another phenyl group to the imidazoles. Okay, nice. Here we observe in the transient absorption experiments the excited state features. This is really the signature of the electrons on the ligands. These are all the signatures when the ligands are, the pyrazine ligands are reduced. Also this feature here is related to electrons on the ligand. And the decay of these features tells, okay, 33 picosecond for that molecule. A little bit different design gives 21, 22. Yeah, okay, nice, but not sufficient, not the nanosecond time range. Yeah, we look back on 10 years of collaboration with Christina Sebri and Philippe Gros. Antonio Monari, who is in the audience, he also contributed initially 25 publications. We studied more than 50 different bidentate, tridentate complexes. Now, this year, we realized that, yeah, one actually has to think of mixed MC and MLCT state. The story of is the electron here or there is not the black and white picture is not correct anymore. We really have orbitals with partial localization either on the ligands, either on the iron. And here 100 picosecond lifetimes were obtained. Renanville worked 3 years on these different complexes, made all kinds of femtosecond studies, including mid-infrared spectroscopy, fluorescence, compared radiative rates, you name it, and that, we now conclude that here we have, together with the computations, it's actually, the orbitals are partly delocalized only over the MLCT. The best result we obtained was with Philippe Gros and Maria Chiara Pastore, who designed this molecule here. And this molecule here with the very extended ligands, they pushed forward the so-called the principle of homoinversion. What you see here is the fact that now the ligand pi orbital is the highest occupied molecular orbital. In particular here, that this state here is 25%, according to Maria Chiara's calculation. 75% of the orbital is ligand-centered, but 25% is iron-centered. And that in contrast to the fully iron-centered lower-lying homos. This is the situation for all the complexes I discussed before. Now, these ligands have higher energies, and the ligand to homo-LUMO transition here is a charge transfer transition, partially from the MLCT, but partly inter-ligand charge transfer. And the result is that we have here now a complex that has the desired lifetime that it needs, 3.5 nanoseconds. This is simply the luminescence decay, luminescence quantum yield of almost 1%. This is one of the really quite competitive among other iron complexes here. But yeah, we cheat a bit because we mix here very strongly the ligand singlet nature into the spectroscopy. Okay, that is to be published. Let me say a few words now about, this is about the transparent solar cells. The motivation is building integrated photovoltaics. What you will see here now is a new development, bringing Grätzel cells into these semi-transparent solar cells into the near infrared, so that the solar cell is completely completely transparent. Here, the dyes that we use are absorbing only near infrared, so the average visible transmission is 76%. Color rendering is great, but you see here very disappointing power conversion efficiency, not more than 4%. Yeah, this is clear. These solar cells will never replace silicon on the rooftop, but that's not the purpose. Here, the idea is to use all the larger surfaces, windows, really use our windows, and for making photocurrent, for making electricity. Yeah, so that was this is the project that we are working on with Fabrice Audobel, Frédéric Sauvage, since now 8 years. Ilias Nikolinakos made his PhD study about this. So the ultrafast mechanisms can be completely characterized here, in particular charge injection rates and yields. We are facing, and I will develop this a little bit, the problem of molecular aggregates. and energy transfer competing with charge injection. But we work here on the full of these small prototypes of solar cells, fully assembled with electrolyte and everything. Yeah, I don't think I have to completely explain what is going on in the solar cells. You have here 2 glass plates. One glass is covered with titanium oxide nanoparticles. That is the design that Grätzel invented. Now we graphed here on the titanium oxide nanoparticles infrared absorbing or near-infrared absorbing dyes. If you excite them, well, they have just, the LUMO level is just above the conduction band edge of titanium oxide. So the electron spontaneously transfers into the titanium oxide, and then the charge migrates through the nanoparticles, is collected by the FTO glass, and the circuit, the electrical circuit is closed. The electrons go back into the electrolyte, and the electrolyte then resets back or regenerates the dye at the end. So we can use one and the same dye several times. You will see in a minute that we will search for the spectroscopic signature of the cation. As soon as this cationic feature arises, we know that the electron has transferred into the solar cell, into the titanium oxide. But the main loss channel are molecular aggregates. And yeah, you will see that in a minute. These are the molecules that Fabrice Audebel and his PhD student Thibaut Baron fabricated. Here now with these push-pull Haagfeld groups, these are the ones that the latest developments not published. But when you graph these dyes on the semiconductor surface, some of them are, yeah, if they are far apart from each other, then they are considered as monomers, but some of them are too close to, and then their van der Waals interactions make them form dimers. And in a dimer, well, you have the Davidoff splitting, the excited state, two levels in the excited state appear, and this lower level is now not high enough in energy for the electrons to inject in the conduction band. So that many of these monomers excited will actually not transfer the electrons, but rather due to energy transfer, and this is super efficient here as we showed by spectroscopy, the energy transfer will rather excite these aggregates. And that was identified by Martin Ziolek already 10 years ago as a main loss channel for different solar cells. When we worked initially on cyanin dyes, we also came to the same conclusion. But the situation is a little bit different, or seems to be different for these new decatopyrrole dyes. The aggregates appear here in the absorption spectrum. So this is a comparison of the absorption spectrum of the near-infrared absorbing dyes. You see here 700 to 800 nanometers. The dyes in solution is this is the full line. But when you graph them on aluminum oxide or titanium oxide, then these additional transitions appear, which are the sign of the aggregates. And the aggregation, the energy transfer can be measured when you look here. This is the fluorescence decay on aluminum oxide, or on titanium oxide you have energy transfer and a carrier injection at the same time. We can work out all the numbers, determine the average energy transfer rate, the injection rate, and we find here, despite the relatively high aggregation number, the injection yield is 80%. And these are the power conversion yields, and you see that the power conversion, is low. Maybe one could improve the device, but it doesn't really change whether or not the aggregates are present. And similarly, so this is transient absorption spectroscopy. after the initial excitation, after 500 femtoseconds, you observe here this feature rising. This is the cationic absorption that prevails actually for a nanosecond or longer. So that really allows us to say, okay, we have here charge injection times of 3 to 15 picoseconds. It's all distributed inhomogeneously because the situation is different. Now again here, no matter how many aggregates we have, the injection yield is very large. So we come to the conclusion, ultrafast spectroscopy reveals all the photochemical scheme for these dye-sensitized solar cells, 50% aggregations. They seem to contribute nevertheless to the photocurrent. It's very likely that they also contribute here to this injection, but that remains to be really proven. And for that purpose, we're now working on the so-called 2D transient absorption experiment, where by making something like a Fourier transformation of the excitation pulses, you can have a very precise or wavelength resolution of how much aggregates contribute to the injection. And some final words now. Yes, all these technology will be integrated or will contribute to in the framework of the Moonshot project that Muriel and Philippe will develop in a minute. 19 different partners. Advanced spectroscopy is present not only in Strasbourg but also in Lille, Paris, here with the Synchro du Soleil, and in Lyon as well. I thank you very much for your attention. Here are the conclusions. We really need the broad choice of femtosecond methods that all the platforms of LUMA allow us to access to terahertz, mid-infrared, up to X-rays emission. Thank you very much for your attention.
Thank you. Thank you. I had a question on the iron complex that you showed at the end with this very conjugated ligand. So you reached a couple of 3 nanoseconds or something lifetime, which is similar to what you would expect for a generic organic dye. So the question, do you know if the MC states are even involved there, or do you get the energy so low that it's really more like the ligand-centered transition that dominate, and you go back to the ground state?
Yeah, we can talk about it in detail. So there are, within the absorption band, you have many different transitions of different character. I didn't show the transient absorption data, but the transient absorption data depend very much on the excitation energy. You can really promote the classical MLCT transition and have in the transient absorption the signature of ligands of ligands reduced, and they live 5 picoseconds only. So there are relaxation channels that involve the metal centered, but these transitions that I showed responsible for the emission, with the charges really delocalized on the organic ligands, they don't seem to be coupled to the MC states.
Interesting.
Thank you. It's very interesting, but we will have to go soon because we have to be at the top of at 7 o'clock exactly. So maybe you can ask questions during the cocktail. Thank you very much.